So now I'm going to talk about the gradient of the curve. Now we've kind of already looked at some of these principles before, but now I'm just going to kind of go into them with a bit more depth when specifically talking about the gradient of a curve. So you can clearly see this is the curve of the function f of x, and it's clear to see that the gradient is changing all along the curve. Because I like to think of it, if you think of it like a mountain, you don't just say how steep is a mountain. It's going to change at every different point you climb it. So this guy is at a really steep bit, so he's having to climb. This guy's at a flat bit, so he can run. So you can't just say one size fits all. What is the gradient of a function? Because it just doesn't really make sense. So what do we have to do? We have to just evaluate at one point. So again, kind of re-illustrating this point, there's different gradients at different points. You can't evaluate between 2 points like you would with like a straight line, because the gradient between P and Q1 is going to be different between the gradient at P and Q2 and Q1. So the gradient can only be evaluated at one point. All right, so again, this is going on to a really important definition. The gradient of a curve at point Q is equal to the gradient of the tangent gradient of the tangent to the curve at Q. So what does that mean? Well, basically that means is that the gradient of the curve, so the rate of change that this curve is changing at this exact point, is equal to the gradient of this straight line, which is at a tangent to this point, so just touching this point. So you could have this anywhere. So if the point was there, this line, so just move around a bit, this line that's completely tangent to this point, so I'll try and get it tangent, will have the same gradient as that curve. And this is a really, really useful definition. Set that back over there. This is a really useful definition, and I'll go on to explain why it's so useful in the next slide.